Yinhai as much time as possible. Please join me in welcoming Professor Yinhai Wang.
Good morning, everyone.
Good morning.
Thanks for coming. So after I got the invitation from Raphael, I was thinking about what's a good topic to talk to you people. I know University of Minnesota is a great school. You have accomplished quite a lot. And I thought maybe I can share some of our experience about artificial intelligence research in transportation engineering. So actually, I'm here presenting several projects done by my students. First of all, I want to introduce a little bit about my lab. My lab is called Smart Transportation Applications Research Laboratory. And this is now under the PacTran Center. PacTran Center is the Region 10 transportation center funded by the US Department of Transportation. We cover 4 states, Alaska, Washington, Oregon, and Idaho. We have 5 research partners. In addition to the University of Washington, we have Washington State University, University for Alaska, University for Idaho, and Oregon State University. So in the recent competition, we added 2 education partners, Gonzaga University and Boise State University. So pretty much you see majority of the university with a strong civil engineering program part of our center. I want to show you some quick background information. You see these red dots showing the size of the population at cities. At this point, we have 7.8 billion people in the world. And we have 28 megacities in 2014, but this will grow to 43 megacities in 2030. So the megacities defined as population over 10 million people. If you look at where we are going to see like the growth, by 2050, the world will have 9.8 billion people. And then the 2 billion people actually is going to be added to city because you see this orange line showing the rural population. It gets stabilized basically after 2015. And this blue line is showing the growth of the urban population. You see actually we're already pretty crowded in the urban area. And the urban area will also have a lot more other challenges. For example, if you look at this chart, from 1980, the roadway supply measured by the roadway lane miles grow only by about 10%. But if you look at the vehicle miles of travel, so in the same time period, the growth is over 110%. This growth is not simply because of the vehicle population increase. So this red line is showing the vehicle population growth over the same time period for about 62%. So you see, this shows not only the vehicle population growth, but also each vehicle driving longer miles at the same time. This gap between the roadway supply and the travel demand is getting bigger. And it shows no indication that the gap will close. If you can imagine that another 2 billion people added to urban area, how the urban area is going to look like. We already see a lot of problems. For example, in this picture, you see the traffic jam. You also see the traffic pollution, right? So we have a lot of questions to answer. For example, what causes congestion and how to mitigate congestion? How much fuel and time wasted in the congestion? How much actual pollution caused by traffic jam? Transportation, energy, and the environment are 3 very important focus areas that the society would care. And transportation ties so closely to the other 2 problems. If you look at the fuel consumption, transportation sector consumes more than 70% of the fuel. And there also research shows transportation contributes or maybe generate about 12 to 68% of the PM 2.5, which is a huge health hazard. Infrastructure-wise, we do see the efficiency challenge, particularly if you think about more people move to the urban area. From another perspective, you see actually traffic deaths increased in 2016 and again in 2017. So the jump was very obvious. Even it stabilized a little bit. You see even a moderated decline in 2018 and 17. Or 15 and 16 was the increase. 17, 18 is about 1.8% decline. But there are still a lot of traffic fatalities. And more importantly, last year, the statistics show pedestrian fatalities reached to 2,227, which is hitting the 28 years high. We need to figure out exactly what happened, why we have a nice declining trend in the traffic fatalities, and we see the increase given that vehicles have much advanced feature for traffic safety. What caused these changes? Maybe you can notice from this picture that a lot of people is actually watching phones when they are crossing the street. Even there are cities like Honolulu have a city law, banning for this kind of activity. It's illegal when you are crossing the street still looking at your phone. But you actually see everywhere people doing this. How can we make our infrastructure more efficient and safer? That's actually a big challenge that's faced by the civil engineers. So in such a scenario, IBM started the concept called smarter cities back to about 7 or 8 years ago. So this is actually the original concept from IBM talking about smarter cities. You can look at this particular chart. It shows the important components for a smarter city. You can see the 3 key things: planning and management, infrastructure, and people. That's in the original idea plan. If you look at exactly how this should be implemented, different cities may launch their different smart city plans. You remember a lot of countries have a kind of a campaign try to promote city to use new information technologies to improve the efficiency and improve the environment conditions, health conditions. US DOT also launched the Smart City Challenge several years ago. There were a lot of cities applied. What you see as the change of this kind of initiative, because smart cities market is estimated to have like $240 billion in like 2025. That's a huge market value. And what people do with this kind of smart city money, normally you see there a lot of instrumentation of sensors. The IoT technology is broadly deployed in the urban area, try to generate the data needed for the intelligence. So in our transportation area, you see the connected autonomous vehicle is becoming a hot topic. A lot of predictions about when the vehicle will come connected and the use of autonomous vehicle technology. What we can think about is the huge amount of data that's going to come with these technologies. For example, this is actually the Intel's estimation for an autonomous vehicle to run for just 1 hour each day, and that's going to be generating like 4,000 gigabytes of data. And you can imagine that's a huge amount of data. Previously, when we do some analysis, when we get an Excel spreadsheet, having some data lines there and do some analysis. But if you use Excel to manage this level of the data scale, it's going to be a disaster, because once you get over 10,000 lines, it's becoming very slow. So we need some new skills. built up to deal with the data that is coming on our way. But how do we deal with this amount of data? That's a huge challenge because when I started my faculty position at the University of Washington in 2002, I did a research, and I was thinking about which class I should offer as my first class. And I was thinking about offering a transportation data management class, and I was studying to see which university may have such a class already. I surveyed every university ranked top 50 in the US and some top universities in the world. I did not see even one university offer a class focused on transportation data management and analysis. So that was my first class. And interestingly, when I started the class, there was only 3 students registered. And my department chair told me, if you only get 3 students, you need to drop this class. So I was very nervous. But the second offer, we got all the 50 slots taken in about 30 minutes. So I think this topic is on demand, but the civil engineering society is kind of behind. This is an important scale that our students should have. But if you don't have such a class, so our student is trained without this kind of data science kind of thinking. And in the future, I think they will find a need to do the training, or they will find a challenge to do the future job that need to use a lot of data. So what to do with the amount of data? So in 2006, I was thinking about building some kind of a tool that we can easily put all these data together, and we can do something with the data and show the value of the data. I communicated with Washington State DOT, and they decided to give me all their loop detector data. So we receive 50 million lines of loop detector data every day, and this data accumulated for over 10 years. So we have a lot of data. So we built a system called DriveNet, and the DriveNet stands for Digital Roadway Interactive Visualization and Evaluation Network. And our student puts these data into our database. We pull data from different sources like the city, the state DOT, online data, offline data. So we use the technology called Fat Server Synclined. We do a lot of work on the server side, or you can consider that could be also on the cloud side. And people can use very simple terminal devices like your phone, your iPad to access the website. And you see what you query, and you got the result on your terminal. The terminal doesn't have much work to deal with the data, just show the result. But on the server side, we do have a lot of work. You see, we get the data, we process the data for quality control, and then put in the database system. Because the data quantity is huge, we have to figure out how to make the query efficient. And then we have this layer, I think is very important, and I would consider this area is going to grow very quickly for scientific research. So this is, we call it data science layer, or the e-science methodologies to be implemented in this area. For example, we can do incident-induced delay calculation. You have a lot of sensors on the network. How do you implement your methodology, pulling the information from the detectors and do the quick computation to respond to the user's query? And at the user side, you get the results from the server side and showing the information you ask for. So here I want to quickly introduce a couple of functions that with this big data analytic framework. For example, if state DOT invests money for improving a roadway, maybe you add 1 lane to a particular corridor, what happens? So this kind of information is pretty hard to quantify before. Maybe when they ask you, after you make the investment, what happened? You can say, oh, improved speed, but how much, right? Because it's very hard to measure from this particular corridor that you instrumented new technology or added 1 lane, because the influence is going to be regional, like multiple corridors, maybe serving the same origin-destination pair could see the change. But using this particular platform, you can select the time and the kind of roadway you're interested, and then you can say, show me the level of service map. And this is basically the level of services, the colors indicating at different level. If you study the heavy capacity manual, you know their level of services from A through F, right? So this is showing the overall performance. You can calculate the index to see, for example, before your project and after the project, during off-peak hour, what happened? During peak hour, what happened? Or maybe when you have a football game, what happens? So this will give you quick information about the network response to a particular project or a particular event. Another function we built is actually try to do the data analysis quick. Washington State DOT published their quarterly green notebook or congestion report. They normally need multiple staff members pulling the data, do the analysis, and they will take multiple months to get that completed. So that delay is one thing, and also the staff member time is another thing. So we built this particular function. You can select the corridor that you want to include in your analysis, and then you can click the button, and in the second, you will see the results pop up. And there's another important advantage for this kind of work. No matter who comes to click this button, you get the same result. If you ask different staff members to look at the same set of data, they may have different standard about which data set is useful, which data set should be dropped. Maybe they consider there's a quality issue with that data. So this particular platform really demonstrates value for this kind of standardized calculation. And you can easily see how a methodology change may change the result. We can also use this platform to do, for example, estimation of the emissions of traffic. If you try a new traffic operation strategy, how would the strategy change the emissions? You can select the corridor, you select the time, and what kind of statistics you want to see. You could choose to see CO or NOx or other statistics, and click this button, and you will see such a chart showing this time-wise and spatial-wise how the pollution changes. I think this is great to quantify how traffic operations may affect the environmental situation. And congestion analysis, you select, for example, the corridor that you're interested in, and also the time period. Click the button, it will generate such statistics like different time and different milepost location, what's the frequency of congestion, and how the speed distribute. So these are just some examples for the efficient side. You could also put the safety data into the analysis, choose the corridor, and see how many incidents you observe on the corridor. And you can also see, based on the traffic safety models, given the usage, how many accidents are expected. And then you can compare the two to see if you have some extra money, where you're supposed to invest, so you can see the big improvement. But these kind of analysis has been common over the past years. This is pretty much you gather the data together and try to visualize the data. Even you see a particular phenomenon, but you may not see why is this. So there are still further research challenges that the community need to address. For example, the data challenge, right? Missing and erroneous data resulted from the sensor malfunctions and other unknown reasons. There's also a saying that big data, if you don't do anything with the data, it could be a big bad data because there are a lot of things mixed together. You need to understand that better rather than just grab the data and put them into your analysis. Methodology challenge, in my opinion, is even much bigger challenge that also have a lot of potential for research. For example, you gather data from different sources. You may get traffic detector data from loops or from like a radar sensor. Those are the point detector data. You may also have Bluetooth measured travel time, and that's a kind of line data. You may also generated like the traffic analysis zones, trip generation, trip attraction data. That's considered the area data. But in your analysis, you want to put all data together, and you are dealing with data not only different in resolution, like a time resolution and spatial resolution, but also this data may be actually measuring different things, but they are related. But how could you make the computer understand the relationship? I think that's a big challenge. And how do we understand the reasons for a particular phenomenon or the causal factors of a specific event, such as a congestion onset or a traffic crash? Why here has more crash in this particular moment? If you use the conventional model, you'll find this roadway segment, try to gather some geometric factors, and try to find how many days this area rained. Those factors are not at the level of detail to explain a particular crash in a more appropriate way. So we have plenty of research topics to deal with on the methodology side. When we try to build the system, like the DriveNet system, we found how do you use these data to do the calculation for the statistics. And those things, we really don't see a lot of suitable methodologies to use. Maybe going back to see why we are lack of methodology to use the increasing amount of data. The traffic people all know this guy. And this is actually the original traffic flow theory started by Greenshield. So he built actually fundamental traffic flow theory, and this is actually his first effort, collecting some traffic data using a camera, and then he studied the relationship between volume, speed, and speed density. So this is actually one of the original publications in this topic. But you can imagine that particular way of collecting data. You have a camera set by the roadway and try to take not only the traffic scene, but also a clock, and then compare to see the time and also counting traffic. So we are still using this kind of traffic flow theory. If you remember, the speed and volume relationship is like this kind of parabolic curve. But there are a lot of dots above the road and relatively consistent at the free flow side. When you get too close to the breakdown side, the dispersion is huge, right? Why is that? And I consider maybe this depends on the data. Not necessarily means at that point they're more like uncertainty. So if you consider there are two sensors instrumented on the roadway, and if you rely on the upstream sensor to observe the congestion, you see vehicle back up all the way to there, right? Depends on where the backup starts. The time lag to observe this slowdown will be different, right? So I guess some uncertainty with this flow theory is likely due to the poor measurement or the data resolution. But now we have a lot of traffic sensors. You see we also have the new data sources like a cell phone, right? There are a lot of research showing how to use cell phone to collect data, Twitter data. We also studied using Twitter message, try to understand a particular traffic crash better, because a bunch of people may be tweeting that particular event. Facebook data, LinkedIn data, Google search data, and even maybe on the street, you see some garbage claim, like Robbins there. They also have the kind of Bluetooth reader there. And if you goes by, they may actually scan your MAC address and try to measure how many people goes by, how long it takes for them to walk around the street. So these things add together, we have this new data stream, so we call that transportation big data. This is a combination of the classical data that we normally have for many years, but these new source of data are much bigger in quantity and much more information rich. If you consider that a bunch of surveillance video cameras give you a lot of data, but this data also take a lot of space. If you don't process the data properly, you may not be able to get the information you really want. We consider AI may be a great way of using this kind of new data sources. This slide shows the brief history of AI. You see, artificial intelligence started in the 50s, but since the 80s, there's the machine learning concept. And then the deep learning started actually 2006. So with all these new methodologies, how we can grab and use for our transportation applications. If you guys play the Go game, you know the robot is now so much better than human, right? So this is the best human player called CEGE. He's a Chinese player. But the AlphaGo master beat him 3-0. Even he's the best player, has no chance to win. The first game was close, the second and the third. And you know, the more you play with the robot, the less likely you win. So, but AlphaGo 0 beat this AlphaGo master 98-11. This AlphaGo 0 means I don't learn anything from human. I learn by playing with myself. So this is the kind of new AI technology that the robot learns by playing with itself, and it can improve very quickly. So, but AI is not perfect, right? So this is actually a most recent event that the IBM's best robot do a debate with the human champion, and the robot lost. We still have a lot of room to improve AI technology and see how they can customize to our usage. So basically, there are several problems with the AI. The first one is the lack of theoretical understanding of the methods. You know, you throw a bunch of data in, you try to use this so-called neural network, and there are a lot of different kind of nodes there. They learn from each other, putting the weighting factors in the connection. But exactly why is this? If you change it to a different data set, how would this internal parameter change? It's pretty hard for us to track those things. And there's also high cost in storage and computation, and difficult to train and no guarantee to converge. Not necessarily you will get an AI model, you will find the converged parameters. But transportation is likely to be one of the first domains in which the general public will be asked to trust the reliability and safety of AI system for a critical task. And this is from actually a Stanford research report on 100-year study on artificial intelligence. There are a lot of attempts right now, for example, autonomous driving, right? They use a lot of different AI technologies from sensing to the route planning. There's also the consideration of using the drone delivery. There's just a lot of things ongoing. And from our side, how we can make the AI customized and used in our application. For example, when we use the artificial intelligence in transportation, like traffic prediction, if you don't consider traffic network features, a general AI model may be built as a universal application. They don't consider your transportation network have the direction feature, right? There's only, like this is the northbound, it goes only one direction, doesn't go backward, and vice versa. Even the two roadways stay very close to each other, unless you have a link. Otherwise, the two roadways shouldn't be interacting with each other. So these features are not in the original AI models. So if you apply those to transportation network, we have to consider how we can customize the machine learning models so it can work better in our application. Here I want to give you an example. This example is actually done by my student. So we can represent the traffic network and their condition as an image, right? So you can look at the traffic flow map. You look at this, you know, okay, where it's congested, where it's not congested. You could also learn traffic as a graph. Let's say from this intersection to that intersection, there is one-way street, you have only one link, directional link. If it's a two-way street, you have bidirectional link. We normally see this kind of traffic flow map. This is based on the data you collected from the roadway network. These sensors generate the kind of information. You see this is actually the milepost, and this is the time. You see the traffic congestion levels. If you try to apply this using the AI, try to understand better how different lane speeds affect each other, how yesterday's speed related to today, there's not a very good model that you can use to regress this kind of relationship. But if you apply a convolution for feature extraction for the traffic network, for example, you could have this image that's representing traffic, and maybe another, this, for example, representing speed, another one represents the volume. You apply this kind of convolution mask, you can extract certain features and combining the features and try to build a connection between different features. You will have a good understanding about how these factors affect each other. For example, this one, we call it modeling multi-lane traffic as a multi-channel image. You have loop detector on each lane, right? And on the same lane, you have at different locations the sensors. This could generate like a flow map image, right? And each lane, you will generate a similar image. And for the loop detector measurement, you have both the volume measurement and occupancy measurement. You could have different kinds of two different streams, right? So if you combine all these things together, you could generate a nice AI model and extracting the features, try to quantify the relationship among these factors. And this particular research that we just conducted has like two streams, and we use the convolution neural network. The attractive features are relations among the roadway segments. Like each roadway segment, you have a sensor on, and the different lanes, how do they interact with each other? So in the loss function, we also consider the volume information, and we consider network outputs vector of speeds of multiple locations at a future timestamp. So all these things you put together, we get pretty nice results. So this is actually a comparison of different methodologies. And the last one is two-stream multi-channel CNN network. So you see the performance using data from different scale. This outperform all other existing methods we tried. And this is a typical customized machine learning method we use for our application. And here you see this is ground truth data, the upper one. This is actually the model data. And you can also see for each lane, the match of the two sets of data is very, very nice. So the orange line is the prediction data, and the blue is the ground truth data. So that's an example for how we can use a customized AI method to make the infrastructure more efficient and predict more accurately. Here I want to briefly mention another research that we use, the video image recognition, video image processing to detect the near-miss events. So this is actually a typical vehicle, a bus vehicle includes like a lot of cameras. In our recent research with the Pierce Transit, typically each bus has 11 cameras. Some of them facing inside, some of them facing outside, the side cameras. How do we make a good use of these cameras so we can make our vehicle safer? So traffic crash is a very rare event, but if you can detect the near-miss events, there are certain relationships. This is from a study showing like about 6.1 million to 13.75 million near-miss events may actually result in about 144 fatalities of traffic crash. And if we get near-miss events, there could be a lot of near-miss events, and that can give us very good insights about what factors in this particular location may be potential safety hazard. I don't want to go to the details of the methodology, but our methodology basically has the components of detection, tracking, and then near-miss judgment. For the detection part, we use the new methods called SSD, single-shot multi-box detector. And we use the tracking methods called SORT. It's all state-of-the-art. But for the near-miss judgment, we actually use a very smart method. It's highly customized, so we can save the computing effort to make it work in the edge device. So we actually try to make the whole thing work in the Jetson TS2 box. Have anybody used that before? So now we have some edge devices. Typical ones are, for example, Raspberry Pi, that small little computer. And the bigger one is like the NVIDIA's like Jetson system. We actually try to do the detection, calculate, track the roadway user, and then try to calculate the time to collision and judge if there's a near miss. And our methodology, I think, have several very important advantages. One is the near-miss judgment algorithm based on the object bounding boxes and the motion profile. We don't need to know like the camera parameters. So you can just grab a video from somewhere and you apply the methodology. It can do the calculation. And also, this is not easy. We achieved the real-time performance for the NVIDIA Jetson TX2 box using the AI Edge technology. And this one will be deployed on the Pierce Transit buses, try to work with another collision detection system from the DCS company, and then we can pass the event from each other and try to gather in this particular bus run how many near-miss events happened and what factors associated with that. That's a FTA-funded project. We actually pulled video images from where we can find them, a lot of them from the website. And then we found actually 80 self-labeled video clips, 30 has near-miss events, and 50 do not. And the data set covers quite a variety of traffic and environmental conditions. We tested our system. We actually tried to evaluate to see some of like an off-the-market system that the company has been using. We evaluate if that is accurate. So I will not mention the name of the company. Very recognized company, like a $20 billion value. We evaluated, actually, these are actually the mistakes that particular system made. Like they consider this is a human using their system. Like this one actually has nothing to do with this direction of driving, but they consider this could be a hazard. And this is the false positive, right? So the last one is the false positive. This is the false negative. These people are actually very close, but the system missed them. But our system was able to capture this. And we evaluated our system. We found our system accuracy is at about 81%. So this is considered pretty good given the camera is on the bus. And the camera is not an ideal camera. And the device is not a real computer. It's a kind of edge device, right, with very limited computing capability. So here I want to show you 2 example videos that shows our customized machine learning effort and the implementation of the system on the edge device, how they work in this kind of real-world scenario. You see this guy? That was like a vehicle to pedestrian near miss. That person was very close. And then we found that particular event. We marked that in red. And then we record this event. We'll pass this particular event to the other system on the vehicle. And they will record their data. And we'll compare the data to see exactly why we detected or they may not detect, or why they detect, we did not detect. And any particular other things related to this. Sometimes it's very easy to detect, there is an event, but one system missed. because one system recorded, right? If both systems missed it, how do we still capture that event? We also need to look at the driver behaviors. We call it the G-force data. If they suddenly make a change, acceleration or deceleration of the vehicle, and we consider there may be something related to that, and we'll record the video around that particular event. That was a vehicle and the pedestrian interaction. So this one is about vehicle to vehicle. You see, that one is quite dangerous, right? So these videos, actually, we just downloaded from YouTube or somewhere. We don't know the camera parameter, but our methodology is able to deal with this without knowing those things to calculate the time to collision. I think that's a quite important accomplishment by my student. So anyway, I want to keep enough time so we can discuss about these things. I want to quickly summarize, what we can conclude. So first of all, I showcased several research projects conducted at the Star Lab, and we found that the AI methodology have been effective in addressing the several issues that we try to address. For example, detecting the near-miss events. If you use the conventional method, because the installation of the camera is quite random, not like following a strict guideline. If you don't use the machine learning to identify where is a car, where is a pedestrian, try to use the conventional method is very difficult. And also predicting the traffic speed, like at the lane level accuracy using the two-stream multi-channel method that I just presented is really working better than the previous methodologies. Another thing we found, and we strongly feel that I should share with the civil engineering community, is that existing AI methods, they are typically developed for more general applications, like the computer science people may initiate a new method, and they consider this could be used for all scenarios. Just like they want to develop a computer vision method, could recognize all kinds of objects. But we care only about the car, pedestrian, bicycle, right, on the roadway. And we can really simplify the methodology a lot to make them work much more efficient for our kind of research work. So there's a huge potential for using the AI methods to address numerous challenges that the transportation community is facing. And we have a lot of data now. And these data, as I said, the classical traffic flow theory or traffic methods are mostly developed based on very small sample size data. Even for highway capacity manual, this is used by a lot of countries in the world. But if you look at a lot of particular methodology, they are based on very small amount of data. Now we have a lot of data. How do we make use of the data? For the traffic network modeling, that's another example. After you develop a model, you simulate, maybe using a couple of nodes, try to see if they fit well. But now we have a lot of data. You can use the real data to compare with your theoretical result. Very often you found they don't match. And it doesn't mean the data is wrong, right? We should reconsider, is our methodology correct? And now with a lot of data, we could work more on the data-driven methods. And there's a lot of potential. And more data will be coming. So I guess it's going to be very rewarding to work in this field. And there are plenty of room for new research. Yeah, so I consider it's also the time for us to use the available data to verify the existing transportation models and develop the data-driven transportation science methods for future applications and corresponding educational curriculum. Last year, University of Washington completely revised our transportation graduate program curriculum. We found actually a lot of our students are hired by non-classical transportation firms like Amazon, like Inrix. It's a big data company. And we consider, why don't we just modify our curriculum to make our students more competitive for the data science kind of job? I talked to some of you about University of Washington Computer Science Department just built a new building, the second building. And our civil engineering department building is still the old one. It's like 70 or 80 years old. When I was interviewed at the University of Washington, the dean at the moment told me, civil engineering is number 3 for a new building. And now it's still number 3. But number 1 and number 2 keep changing. So, and I just wonder, what should we do to make this different, right? So if you provide the kind of talents needed by those big companies who has a lot of money, you are likely to get better support. So we make our curriculum completely revised. So our student, if they finish the master's program, they could easily take a data scientist job because they are very well prepared. So I mentioned about the laboratory, like at University of Washington, my STAR lab. There are a bunch of other labs. So certainly, we look forward for talents who are interested to join us. You are greatly welcome. We have a lot of data. We certainly have a lot of funded projects. So the project I presented today actually is funded by WashDOT, FTA, and the PacTran Center. So the 2 persons I want to recognize specifically are Ruimin Ke and Zhiyong Cui, these 2 students, PhD students, who actually conducted a lot of work for the projects that I just presented. So that's pretty much what I have for today, and I want to open up for questions. Thank you.
Thank you very much, Professor Wang, for the talk. Thank you. Do we have any questions? We have a new microphone system here. Let's go to the back of the room.
Hi.
Quick question. So, I want to congratulate you about the system that you developed for WashDOT. Congratulations on the fact that it is open and available on a web server. Well, we have developed similar systems. California has developed similar systems, PEMS, but they're all hidden behind firewalls. So they're there, but nobody else can use it other than the DOT. My question is that these systems are possible right now because the data that they're dealing with are relatively manageable in size. When you, in your earlier slide, you said that the Intel estimation is that one vehicle will produce 4 terabytes of data a day.
Yeah.
But even if we don't consider all the LiDAR sensors, but we only consider the connected vehicle basic safety message, which is something easier, still, if you consider it on a network-wise, we're talking about petabytes of data in a very short amount of time.
Yeah.
This cannot be saved. There is no way that you can store this.
Yeah.
So how can you achieve the same type of benefit analysis of historical versus future and current, but not run out of space very quickly?
That's a very good question. Actually, this touches upon another new topic that we are working on. Is pretty much the edge computing. The second project I mentioned actually have that kind of feature. The reason we built an onboard processing system was actually different from the original plan that written in the proposal we submitted. At the very beginning, we were thinking about gathering the data to the lab, and we do the analysis there. So at that point, Microsoft was part of this, and they were thinking about providing the cloud service support. And later, we discussed about the amount of data. If you consider you have 11 cameras on a bus, we may do the experiment for 2 years. And if, not to say 24 hours, even the hours when the bus is operating, you can imagine how much data that we need to consider. Storing the data is going to be expensive if you use a lot of cloud space. And that is only one part of the issue. Communicating, transferring this data to the cloud is another big cost. And then we suggested to do just the onboard processing. We only record video when we see an event associated with it. So we cut down this maybe 95% of the data. So only 5% of the data will be stored in our Jetson system. And when we see a network connection and the bandwidth, we'll send the data to the lab for archiving. I guess in the future, there are 4,000 gigabytes of data per hour. If you assume that vehicle run only 1 hour each day, that's the amount of data. But that particular quantity of data will not be easily accommodated by this kind of methodology. So edge computing is getting very popular now because the needs to do some reduction before you really go to the cloud. And we have another example. Actually, we work with the Sound Transit, try to do the parking detection. And if you use the AI method, we use the Raspberry Pi on site. This is just not enough to do the detection. The computing power is not enough. So what we did was try to identify the vehicle area, like the bounding boxes, and only transfer the box content to the server. And then we computed the server side to confirm if this is the same car. Because we want to see this parking slot is occupied or not, right? If it's occupied, okay, we know there's some car, but is it the same car from the last detection? So there's just a lot of topic going on that side, but I believe that may be an easy way to deal with that big data quantity challenge. Okay, any other questions? Gary?
Yeah, this is a very informative talk. Here's a question. When I'm thirsty, okay, I go to the faucet and I turn the water on and I get some water and I drink it and I turn it off. I don't leave the faucet running all the time. Mm-hmm. One possibility, okay, would be that instead of collecting, say, all the loop detector data and storing it, what you do is the user has the option of turning on a data faucet. All right, and for instance, individual vehicle pulses and things like that, and even finer level of resolution could be possible, and I let that run until I have enough to do what I want to do, and I turn it off. Could you speculate about that kind of possibility sometime in the near future?
I think that's another great question. Actually, using the DriveNet as an example. So when I tried to build this DriveNet in 2006, there was no such big data concepts. I just feel with so many loop detector data, you cannot use Excel to do it. Not everyone knows how to use SQL Server. And how can we build a kind of tool people can use? And maybe some smaller cities, you don't have a traffic engineer. You have no person to develop a traffic information system. If you build this kind of general platform, that small city can just upload the data following the data format, and their city become part of the overall traffic information system network. And that's for showing the information side. For doing the analysis side, if you are a consulting company, you only need data for maybe a couple of days from that particular street. They can just come here to download that data set. The storage media is getting cheaper and cheaper. So if we don't store, for example, loop detector data, we may feel regret because later, due to some reason we need the data, it's not there. But certainly, not every company, every individual, every professor will need those things continuously. I constantly feel like the challenge, the pain, because the data fill my storage space very quickly. And I keep buying more and more data storage disks. And there's some company like Amazon say, hey, you can transfer the data to our cloud, and we can give you a kind of project support to do the transfer. Later, we ask our student to do a check to see what happens if I run out of money. I cannot afford paying the online service. And they say, when you transfer the data back, you need to pay. And it's free for you to give data, but when you run out of money, you want to bring the data back, you have to pay, and that's the moment you have no money. So, and then we thought, okay, let's just keep the online thing. We do small testing on online. Unless I see a constant money supporting that, I can put this online. Otherwise, even the server side, we have more work to do. Like you need to provide the server environment for people to use. But that's a safer way. At least even I run out of money, if the server is still good, I can still keep the system running for maybe 5, 10 years. But certainly, I think the future will be we go to consume the online data resources based on our need. But somebody got to provide that kind of service. Any other questions?
Time for maybe one more short question, if there's one more short question. Otherwise, I was wondering if you could maybe comment. You mentioned on sort of the lack of interpretability of machine learning. So on the one hand, you showed like there's great potential for machine learning type applications in civil engineering and specifically in transportation. On the other hand, you mentioned that there's this lack of interpretability, or you don't. And so I'm wondering if you can maybe comment on that trade-off for like safety critical systems. How much can we rely on machine learning based systems when we don't necessarily know how, when it's somewhat of a black box, and sort of, I guess, where do you see the space for that?
Yeah, I think that's certainly a question every researcher that use AI should think about. It's not just grab a common tool and just apply that and then believe it. To get a credible result, I think you need to look at two things. The data quality itself, right? If the garbage in and it's garbage out, no matter how wonderful your model might be. And even you have an AI model, a lot of people tend to use AI model to compare with a regression model. I think that's quite unfair because AI model, you use so many parameters, right, to do the kind of regression. But when you do the R-square adjustment, the more parameters you use, the lower the R-square value, right? So if you accomplish the some level of fitness. But for AI, you just don't know how many parameters get involved. And if you try to customize the model more toward the reality, like a traffic network has direction, it doesn't have the interaction at every intersection unless you have a link between the two, right? If you consider these things, you can reduce the flaw in your methodology. Otherwise, you may see actually the contribution of the downstream variables to the upstream. Sometimes it has, but in most cases, the upstream affect the downstream predictivity, right? So I think if we don't try to understand what we're doing, even we apply AI, try to customize it to fit our problem in the way we want, you do not know what kind of mistake you may be making. When you are enjoying maybe a higher accuracy, but actually there's a big problem hiding there.
So there's still room for domain knowledge.
Yeah, even you do the customization, there may still be that problem, but the chance is just much lower. Okay, so
well, thank you very much. Let's thank our
thank you.